Yeah. When I turn it on.
Yeah, I'm gonna wipe it after you did. You know.
Oh, I planned on it. It was just turned off at the moment. Thanks, I was waiting for when it was time to begin.
Okay, well, we'll go ahead and get started. I guess I should say something formal, but since it's only us, I don't need to say anything, but thank you for tolerating the change. I know it threw a lot of people off having to go on today instead of on Monday, but typically when the president calls a forum, you typically have to go, and I didn't feel that it was worth worth letting just one person call. So that was a third person. So with no further ado, we will begin our final presentations in our senior seminar course. And first we have Mr. Adam Hurdle. All right, all yours.
Good morning.
Good morning.
My name is Adam Hurdle. I'm a fourth-year math major here at Florida A&M University. I've been working on a project for molecular dynamics of an argon atom, and my advisor has been Dr. Ajit Gunarante. Today, I'd like to take you through my project. I'll be talking about what it is my hope that you'll gain a greater understanding of what molecular dynamics is through this presentation. So I'll be talking about the protein folding problem and its significance to molecular dynamics, and what exactly molecular dynamics is and why it's important. We'll talk about the laws of motion, the empirical energy function, the basic simulation process, the least action principle, the Verlet algorithm. I'll also be giving a brief history of Argon, its simulation, and I'll share with you my results and future plans. So, why molecular dynamics? To understand molecular dynamics, it's important to understand its applications. So, we consider the protein. Proteins are what drive all biochemical reactions, and each protein is made up of 20 basic building blocks of life known as amino acids. Amino acids are just the subunits of a protein. So if we, excuse me, because amino acids can be connected in arbitrary sequences, the amount of space amount of proteins that can be created is exponential. In fact, it can go up to as many as 2,050,000. The chain of amino acids can take on different shapes, and those various shapes allow the proteins to take on different characteristics. Here on the bottom, I simply have an illustration of two amino acids interacting with each other. Whenever an amino acid reacts, it always has a byproduct of water, H2O, and then it will create what is called a dipeptide. Many dipeptides come together to create a protein, which is illustrated here as a side chain or the backbone. Proteins are what make up our muscle, bone, hair, skin, blood vessels. It's estimated that the human body may contain over 2 million proteins found in the approximately 100 genomes of the body. As of 2007, scientists have sequenced the human genome, which is the blueprint for all of proteins in biology. But the real question is, how do we understand them, and how do they work? In order to accomplish its purpose, first a protein has to take on a particular shape, which is called a fold. Now, they put themselves together, they self-assemble into this folding process, and you can see an example of that here on the bottom left-hand side. Sometimes, when they're folding themselves, they misfold and create a different shape than what they're supposed to create. Example here on the right. And that can cause many problems. Diseases such as Alzheimer's, cystic fibrosis, BSE, or mad cow disease, are an inherited form of emphysema, and even many cancers are believed to be a result of this misfolding. So proteins not only self-assemble, but they do it so quickly that we can't even see it. So it happens, we can't see it with the naked eye. It happens as fast as a microsecond. In fact, there's not a single known experimental method to observe the protein folding. Therefore, the only way that we can actually see it happening is through simulation processes which is where molecular dynamics can be extremely useful. However, it must be noted that it can take a computer a full day to simulate 1 nanosecond of a protein folding. Or since proteins fold on tens of microseconds of time scale, it would take a computer to 10,000 CPU days to simulate 10,000 nanoseconds. That's 10 to the negative 5 seconds worth of simulation, and it takes approximately 30 years to actually simulate it. So that's one of the problems that we are out to solve, how to actually speed it up. In fact, to solve the protein folding problem, we need to break the time barrier. One way to do this is to develop a more efficient algorithm. Simulating milliseconds of folding time could unlock the mystery of how proteins fold. Here are just a couple of quotes from Peter Coleman. He's a professor at the Pharmaceutical Chemistry at the University of California, San Francisco. And these are just to show how important it would be to solve the protein folding problem. According to him, the protein folding problem is still the single most exciting problem in computational biochemistry, and to be able to predict the structure of the protein from just the amino acid sequence would have tremendous impact in all of biotechnology and drug design. I've given here a picture of each of the amino acids and their structure so you can see the amount of atoms in each and their different configurations. And this is a graphic illustrating illustrating where we've come over time with molecular dynamics. The important thing to note here, though, is that though we've made tremendous strides in molecular dynamics, as you can see here in 2002, just over approximately 5 nanoseconds worth of simulation in 90,000 atoms, then even though that's a tremendous slide from 1978 where we only had 3 atoms and a few nanoseconds, the important thing to remember is that the body has an estimated 2 million proteins, and the longest of which is 26,926 amino acids. And because the 20 amino acids can be connected in arbitrary sequences, producing exponential numbers of proteins, if we assume that each protein had an average of 100 amino acids and each amino acid had 15 atoms to simulate, then we would need to map 15 times 100 times 2,050,000. That kind of gives you an idea of how much further we still got to go. So what is molecular dynamics? It's a computer simulation method used to predict the motion of particles over time. And these motions are, of course, governed by the Newton's laws of motion. As already stated, the molecular dynamics is governed by the laws of motion. Here I have the first law of motion written by the second law of motion written by as mass times the second derivative with respect to t. This is by time of x equal to the negative gradient of the phi function, which is energy, which we will talk about more in a minute. It's the negative gradient of the force function phi. Because the acceleration of the second derivative is the position function, also the second derivative of x is rewritten as represented by the finite difference here, which is a numerical method of approximating the finite difference of the second derivative of mass is a diagonal, is written in a diagonal matrix of 3n by 3n. The x is a position vector given for each of the atoms, the x, y, z coordinates. And then, of course, x naught is just the first position at time 1, and v naught is the velocity at time 1. Here we have the potential function phi. This is the empirical energy function, which is made up of the sums of each of the types of energy that can be produced through the interactions of the atoms. Down here at the bottom, you see that it's a different example of how these atoms interact and why there's different types of energy produced. For our particular project, we're going to be working with argon atoms, so therefore we're going to be working with just the non-bonded form. and therefore its potential energy. So the basic process of molecular dynamics is represented in this flow chart. To begin with, we need preliminary work, or the Cartesian coordinates for each of the Cartesian coordinates must be defined. After determining the coordinates of the values of each molecule, total energy as a function of the Cartesian coordinates is computed by evaluating the individual atoms of the energy equation. All the dynamic simulations begin with an initial structure that may be minimized. The minimized structure represents a molecule at a temperature close to absolute zero. Then we heat the molecule, which is accomplished by assigning initially assigning random velocities according to a Gaussian distribution appropriate for that low temperature, and then running dynamics. This temperature is gradually increased by assigning greater random velocities to each atom at a predetermined time interval. Equilibration is achieved by allowing the system to evolve spontaneously for a period of time and integrating the equations of motion until the average temperature of the structure remains stable. This is facilitated periodically reassigning velocities to the appropriate desired temperature. In typical simulation, trajectory traces the motion of the statistical properties of the system become independent of time. Just as with energy minimization, provision is made to update the non-bonded and hydrogen-bonded list periodically. Additional options are available, making the dynamics facility quite flexible. And quenching is an optional portion of molecular dynamics to slowly remove all kinetic energy over time. The least action principle is it states that actual trajectories and velocities of particles in the real world will make the action extremal, or it'll tend to maximize or minimize. In this case, we're talking minimization. Simply put, it says the natural state of affairs for a particle will be minimal in position and not necessarily at zero. Here we have a theorem relating to the least action principle with Newton's law of motion. Theorem, let L be continuously differentiable function and let X be the solution of each of the least action problem. Then X satisfies the Euler-Lagrange equation as stated here. And then it follows by a corollary showing that if we let L be X prime transpose mx prime over 2 minus the energy function, where m is the mass matrix of the molecule and p is the potential energy function, then a necessary condition for X to minimize that action is that mx is equal to the negative gradient of the phi, showing that there is a relation between Newton's law and the least action principle. And to illustrate the least action principle, is the waterfall, simply when the river gets to the edge of the waterfall, it doesn't just stop and stay there, it falls over, showing that the water wants to be at the lowest position. And if I poured a bucket of water over a contoured line right there, the water wouldn't flow up the line, it would flow down and into one of these dips, depending on how much water I poured. It could go here or it could go there, depending on where the strand will. To further illustrate these points, if we let these 5 balls represent move over a period of time over this contour, then they will eventually fall into the minimal position as such. The Verlet algorithm is represented here in both its forms. As you can see, we can find the k+1 term of the position function x of an atom I, given the position function of the kth atom and the k-1 atom, which is given in terms of 2 times the kth atom minus the k-1 atom plus the time step squared times the force of that atom divided by the mass. And again, this is the velocity version of the same equation, algorithm. So for my project, we chose molecular dynamics of argon because for us it would be the gateway into understanding molecular dynamics and moving forward into into simulating more complex systems later on, such as the protein pooling problem. So I'd like to give a brief history of the argon atom, which is found at number 18 on the periodic table. The atomic weight is 39.948 moles. It is a member of the noble gas group, and although it was discovered much earlier, although it was suspected much earlier, it was actually discovered in 1894 by Lord Rayleigh. Here is the energy function phi, and because we have argon, which is a noble gas, it's an inert gas. Its octet, the outer octet is full, and so therefore it won't react with other atoms. So when we're talking about the energy function phi for argon, we have to deal with only the non-bonded form. So here we have that represented by the Lennard-Jones potential energy function, the 12-6 form of that function. Since the force is represented by the gradient of this energy function, we then take the gradient and represent it here by the force field, which is the sum of the atoms acting on that. And here we choose to scale our mass for this function in order to control the simulation process. And we're scaling it to, we're saying that the mass will be equal to 48 epsilon sigma, which we're using epsilon as our energy and sigma as our length. And since we're doing that, we're going to scale the mass, and when we do that, as you can see here, this is 48 epsilon, where that means we're just going to have mass, we're substituting mass in there so that it cancels stuff out later. For the simulation of argon atoms, we begin with the global minimization position of the atoms, the configuration size. We simulate the initial velocity of the atoms, and we push them slightly, which is where we get our initial velocities. When we just push them in a random direction, no more than 0.5 angstroms. The value of the direction or push is determined randomly, and for the simulation we use the Verlet model and the time step of 0.2 over a 100 iteration process, done several times using multiple trajectories. In testing, I had anywhere from 3 to 150 atoms. And finally, we collect the data for analysis. And to help understand that just a little better, we have a flow chart just to show you how it's working. We start with the initial values already in their minimal state. We have a minimized geometry. And we add to that the initial velocities, which is just changing pushing it by that 0.5 angstrom. Remembering to consider the constraints of the system. If two atoms get too close, they can't be occupying the exact same space at the same time. So we have to consider that and not calculate this force. Also, if it gets too far away, we don't want to calculate this force for that. Then, as we do that, we'll integrate using the Verlet equation. Then we'll assign the new coordinates over the time, and then we'll calculate the thermodynamics and gather our information for analysis. Here I have this is one of our simulations using a program called VMD, Visual Molecular Dynamics, and Video Match. You can take the information gathered to create video visualization. It must be noted, this is only over a very, very quick time. Got it on repeat so you can see it constantly moving. This is the 3-cluster atom, and you can kind of see they're equidistant apart. They're moving with each other. And this is the 13-cluster atom, just to kind of give you how it all works together. For final thoughts on future plans, I'd like, even though this project is ending, I'd like to continue the research and develop the necessary skills of programming to eventually move forward and work on finding a solution to the protein folding problem. And I must note, this project was guided by Dr. Edith Gunaranek, and I owe him many thanks, not only for assisting me in the project, but for helping me to develop new interests and to broaden my knowledge in the field of mathematics and its application. I also want to thank you, the audience. You've been great, and this time I'd like to open up if there's any questions.
Very good.
Could you just give a brief answer why the 13 atom moved much slower?
Yeah, the time with the 13 atom simulation, what you're seeing, it's the 3 atom simulation. The time step was not very good. I didn't get the opportunity to make it extend out longer than I wanted to. So because it was such a short time frame that you were looking at, it was moving a lot faster than what we actually hoped.
I was hoping that would be it.
Any other questions?
Or comments?
Or comments?
I was just your comments now, or is it just questions?
That was clear on this semester.
Thank you.
Thank you, Adam.
And I want to add a little comment about this work. This is not, I believe, that one semester project.
Correct.
There's a lot of computation involved with it, but I know we both struggle with understand this special program. So I try to make sure that he understood what this is doing. For him, understanding application of
Next person can be
mathematics
getting ready.
plus understanding the computer program together, especially this system grow when you simulate because the arrays that we use is not as simple as the regular programming we do. So we struggle with memory and computing power, and I think we made a good something that we all can say.
He did very well. Very well. Very well. All right, so next we're going to have Mr. Hardaway, who's getting ready. Huh? I feel confused.
Because math used to be maths. See why I'm looking for you most of the time? Jeff, I like you did Clark Kent right now.
Yeah, I got it.
Whoa, Bruce, did you stop the recording?
Yeah, I'll give it to you after.
You know what? I did have a comment, but
Bruce. Bruce.
No.
Wait, Bruce.
Final presentation.
Bruce.
Email a comment.
Bruce, did you stop the recording?
yes, I did.
It has the red button up there.
And what time does it show at the bottom of it? Does it say like 20 minutes or something like
23.
that? Oh, stop it. And then,
Yeah.